Hello, I'm Dr. Mark Taylor and I'm a lecturer in civil engineering. So welcome to Railway Engineering. This is Unit 3, Railway Track, Part 2. In this lecture we're going to look at the sleepers, the fasteners, the rail pads and some of the plant and equipment that you can use to assemble railway track. So in this lesson I'm going to introduce thermal related rail expansion and how we calculate that. I'll also outline the 4 types of railway sleeper that we can use. I'll also provide some details on the fixing systems between the rail and the sleeper. At the end of this lesson, you should be able to calculate the change in length of a rail due to variations in temperature, recommend methods of counteracting the effects of thermal expansion of rails, assess the most appropriate type of sleeper and fastener for a particular track application, and describe the principal benefits of slab track over traditional ballasted track. So we'll start off with having a look at rail thermal expansion. Materials generally expand as they get warmer and contract as they cool, and rail is no exception. The extension of a bar of material, expressed as a proportion of its original length when the temperature raises by 1 degree, is called the coefficient of linear expansion. The coefficient for rail steel is usually taken as 0.0000115 per degree Celsius. For a rail of length L, the change in length for any change in temperature is given by the delta L, i.e. the change in the length for a given temperature change, is equal to the coefficient of linear expansion multiplied by the original length multiplied by the change in temperature. So let's consider a worked example. A continuously welded rail was delivered to site. It was 0 degrees when it was delivered. When the rail was delivered, it measured 120 meters. So how much longer is a rail going to be on a day when the temperature reaches 30 degrees Celsius, which is quite a rare occasion for a day in Scotland? So if we do the calculation, the extension is 41.4 millimeters. Let's now have a look at compressive strain. When the rail is installed, any change in length due to the temperature variation is resisted by the fastening system and the ballast. This resistance results in a force F. From Hooke's law, for a rail with cross-sectional area S, the change in length due to such a force being applied would be calculated as shown below. The total stress and strain will be a combination of these opposite forces, as shown. For no expansion to take place, delta L total must equal 0. So let's have a look at another worked example. In this case, a section of UIC 60 rail is installed on a cold day at a temperature of -5 degrees C. So what force would be generated as a result of the air temperature being 28 degrees centigrade on a very hot Scottish summer's day? And here we can see that the force would be 583 kilonewtons, and this would probably cause the rail to buckle. So here you can see an example of rail buckling caused by excessive summer temperatures. This was taken just near Wishaw, outside Glasgow, on the 28th of May 2018. In continuously welded rail, the rail is artificially extended and fixed down in tension to prevent this from happening. As a result, the rail does not go into compression until a predetermined value is met. This is known as the stress-free temperature, and in the UK is typically 27 degrees Celsius. Consequently, the compressive force is halved on even the hottest day. The rail can either be stretched by warming or using what's called a tensor machine, shown on the right here. The calculation done to determine tension based on rail temperature, neutral temperature, length of rail, etc. on the day of installation. In jointed track, a build-up of compressive force is prevented by expansion gaps at the rail joints. Special shims of predefined thickness are used when laying jointed track to achieve an appropriate joint. The shims are inserted before fish plates are assembled and bolted. A rail thermometer can be used to determine the rail temperature. Track can also be configured to accommodate expansion using what's called an adjustment switch. The switch comprises two tapering rails abutting each other. These can accommodate a significant amount of expansion and contraction. They're usually used at switch and crossing layouts, adjacent to bridge decks, or where different rail sections join. Painting the web of rails white can be undertaken as a risk mitigation measure. The rails must be painted annually prior to the warm season. This is most common where rail tensioning is difficult, e.g. near switches and crossings. This can result in a 5 degrees Celsius lower rail temperature in direct sunlight. Here you can see a junction just outside Haymarket Station, where the rails, approaching quite a complex junction, have been painted white to mitigate against thermal expansion. So let's now have a look at sleepers. These are sometimes referred to as ties because they tie the rails together to maintain gauge. So where does the word sleeper come from? The term sleeper comes from the description of a horizontal timber used for distributing loads. In building construction, it could be a long wooden, metal or stone piece lying horizontally as a sill or a footing. The term sleeper can also be used to describe a railway carriage, which is used for passengers who travel overnight, and hence the term sleeper. In this context, sleepers are referred to the horizontal timbers which distribute the loads from the track down into the subgrade. A sleeper must spread wheel loads over a large area to ensure ballast and formation is not overstressed, to hold the rail to the correct gauge and inclination, prevent the rail from rolling over sideways, moving laterally, moving longitudinally, and insulate the two rails electrically from each other. Timber is a traditional material for sleepers. It still has many advantages, even today, including ease of handling, good resilience, and good electrical insulation. Hardwoods such as Jarrah can be used in untreated form. Softwoods such as Douglas fir or Scots pine are impregnated. Impregnation involves incision of wood and pumping in preservative under pressure. A timber sleeper can last from anything between 15 and 35 years. Monoblock concrete sleepers are poor under tension. Pre or post stressing is applied to develop strength. They're moulded to include an angle for the rail seat. They are shaped to develop maximum strength at minimum weight. Rail fastener attachments are often included in the manufacturing of these. They require care when handling and specialist lifting equipment. Their heavy weight is beneficial as it resists movement better. Twin block concrete sleepers are two concrete blocks cast around a steel tie bar. They're lighter, so they're easier to handle. They're more prone to movement in ballasted situations. Rail fasteners are often included in the manufacturing process. They're good for light rail applications and can be cast into concrete, e.g. these were used in the Channel Tunnel. They were also used in the Edinburgh Tram project. Steel sleepers are generally sturdier than timber. They're less expensive than concrete. There's less reliance on the ballast, but they're susceptible to corrosion. They're best for light traffic and for lower speeds. Slab track is a track constructed on a reinforced concrete slab. It's generally more expensive at the outset, but there are large maintenance benefits through the elimination of ballast. They provide good ride quality and are applicable for high-speed rail. They're useful in areas where track stability is important, and in particular to maintain structure gauge, e.g. tunnels. They can have issues with noise and vibration. So we're now going to have a look at some of the rail fasteners that can be used. So there's a need to connect the rail with the sleeper. This is to resist creep, the longitudinal movement of the rail relative to the track bed, and also resist buckling. Problems include vibration causing loosening and elasticity required to resist creep. In terms of performance requirements, these are summarised below and include supporting vertical loads, transmitting these loads to the sleepers, maintaining gauge and inclination, resisting creep, allowance for thermal effects. They must also be an insulator to allow track circuits to be maintained. They must also be easily installed and removed for maintenance purposes. And most importantly, they must be economic, i.e. value for money. The elastic rail spikes are driven directly into the sleeper, which is usually timber. They can be used with or without a base plate. They have limited control over the toe load, so have low creep resistance, which is not ideal. RN or NABLA fastening systems manage toe loads by tightening up a nut. The steel element acts as a spring. Voslov fastening systems use a coiled steel spring, and they're held in place by a coach screw. Let's now have a look at some Pandrel rail clips. These are similar to the Voslov, but coach screw is replaced by a fixed element, often part of the sleeper. The clip slides into place through the hole. In position, the clip bears on the rail foot and sleeper. The fixed hole becomes a fulcrum. The clip is deflected on insertion and generates a predetermined clamping force. E-clips can be inserted using what's called a pan puller tool. It's very labour intensive, it's a slow process. It's good for small tasks such as isolated sleeper replacement. If a large number of E-clips have to be removed, there are machines available which mechanise the process. They use hydraulic power and hydraulic rams to extract the clips. The figure shown below shows the clip in situ and the machine mounted, ready to extract one of the clips. Typically there'll be a cage around this area to catch the clip if need be. Pandrel recently developed the fast clip system. It's a pre-assembled system where the components remain captive in the sleeper. Once the sleepers are laid and the rail installed, the clip is simply pushed into the rail by means of a simple drive action. It can be used for concrete and steel sleepers. The system is optimised when used with a range of Rosenquist clipping machines. You can also get a manual puller, so if you have to replace a single sleeper, you can then manually extract one of the fast clips and put it back into place. In terms of maintenance, it's important to look out for decay, for example rot around lock spikes, and relocate them if necessary. You must ensure that coach screws are tightened, inspect for wear or damage, and you must check the insulators. The steel-to-steel contact will affect signalling and track circuits. So now we're going to have a look at rail pads. The function of a rail pad is to cushion the impact of vertical loading by providing a conforming layer between the rail and sleeper to achieve an even pressure on the rail seat area. They act as a vertical spring to reduce transmission of vibration and impact from rail into the sleeper. They also act as a horizontal spring to assist in the distribution of traction and braking forces. The materials used for pads is important. They need to provide good electrical insulation, last for a long period of time, have consistent properties over different temperature ranges, be resistant to abrasion and fatigue deformation, and also resistant to the environment, for example the moisture that they're exposed to, UV light or any oils, etc. Common materials include ethyl vinyl acetate, high density polyethylene, and polyurethane. EVA, HDPE and polyurethane pads are effective on high axle loads at low speeds. At higher speeds, vibration and impact forces can still become damaging. Special pads have been developed to deal with rapid shape deformation and recovery. The objective is to reflect force back into the rail as quickly as possible, without absorption or damping. The image on the left shows a Pan 2 plate recovered from a timber sleeper at Bo'ness. Soft rubber pads are used on the TGV and Shinkansen. The volumetric compressibility of the rubber is virtually zero. If a pad is in a confined space, then unwanted heat and abrasion will result. The use of grooves and pimples provides space for deformation. The assembly of track has developed from being a very labour-intensive process to a process which now sees lots of automated plant, equipment and machinery being used. Track lane equipment is extremely complex, and it's quite difficult to explain how these machines function and operate from a series of photographs. So what I've done is I've put together some YouTube footage showing the machines in operation. Pay careful attention to each of the activities, look at the rams, look at the end effectors, and look at the tasks that they're performing. Also, keep an eye out for operators. They're often hidden inside the machines. You'll also notice that there are a number of engineers who observe the machines and the various tasks and keep eyes on the machine at all times. This is to look out for problems and issues and to help try and resolve these as quickly as possible. So in the next lesson we're going to look at the formation of track. We're going to look at the ballast, the earthworks, the subgrade and also the drainage requirements. So that's the end of Unit 3 Railway Track Part 2. Thanks for listening and bye for now.